Hello everyone, welcome to Modeling Methods in Mechanical Engineering, and we are going to continue our discussion on field theory and the different vector operators and now integral operators as well, and integral identities that apply to fields. So let's get right to it, and modeling methods in ME. And let's discuss Gauss's divergence theory. Or theorem. Okay. Well, we know what divergency is now. Divergency is a scalar operator. It's an operator that operates on a vector field and turns it into a scalar. This person, Gauss, which was one of the greatest mathematicians of all time, a very precocious person. When he was 6 years old, he came up with the first formula. And even though he lived in the 18th century, I consider him to be the father of numerical methods, even though there were no computers in the 18th century. A lot of the things that we use in computer algorithms are due to Gauss, even nowadays. So among the things that he did, including the electric field theory and his divergency theorem, and numerical algorithms, quadratures, integration quadratures, all kinds of things. He was notable for not publishing everything. He would just write notes and keep them on his desk. And then sometimes people would come to him and say, "Hey, I came up with this thing," and he said, "Oh, I already did that. Here it is." Okay, so he didn't publish a lot, but when he published, he actually made a huge difference. He was also a great mentor to many other mathematicians, like Riemann, for example, who actually changed geometry forever. He changed Euclidean geometry to non-Euclidean geometry, so among other things. So what he did was the following. So if you recall the definition of divergency, let's just go back to that strange definition of divergency, the original one, where we say that the divergency was the limit when the volume or the region goes to 0 of 1 over the region times the closed contour integral, which is where gamma is the surface that surrounds omega, of v dotted into n, the gamma. Okay, and from that, remember, we did the trick of the parallelopipe and just make that region a cube and then shrink that cube to 0 and so on, and we got that nice looking leading to this nice looking formulation. This is a divergency is basically equivalent to writing the nabla operator dotted into v, and the dot is really important, remember, because that's what makes this a scalar operator. And again, what we're going to do now is just assume this is the region omega, which can be again two-dimensional, three-dimensional, or even one-dimensional, just a line. And then what we're going to do is pick a point here on this region, right? And we're going to surround that point again by the trick of that little parallelopipe. And we're going to call that parallelopipe a piece of omega, the ith piece of omega. So it's an infinitesimal piece. And well, this is point pi. Okay. And what we're going to say is that omega is simply the summation from I equal 1 to n, or as many cubes as we can fit into this geometry, of the omega I. So the omega is the summation of all pieces of omega. That's pretty simple. So then we can say that the divergency of v, again, v is some I don't have a green or another color, but v is some sort of field that traverses here. It's a vector field. All right. So the divergency of v at point pi is equal to the limit when delta or d omega I goes to 0 of 1 divided by d omega I the contour that surrounds omega I, which is now easy to figure out. Okay, because the contour of a cube is just 6 faces. And then what we're going to do is just simply say, if we revert this thing, we're just going to take this d omega I and pass it to the other side and add them up. So the summation from I equal 1 to n to all the possible bi's at all the points, or divergences of bi's at all the points, multiplied times delta gamma, or d omega I, is equal to the summation over I equal 1 to n of all the possible contour integrals over all possible cubes inside that region, v dot n d gamma I. And as n goes to infinity, as it should, right, because there's an infinite number of infinitesimal little cubes that fit into this region, then this will simply look like this. It's essentially the integral over the entire volume. This is what a summation is. Summation over an infinite number of n's is an integral of the divergency of v, the omega, is equal to the integral over the entire. You can actually make the argument that the summation over all the cubes, if you integrate over all the faces of all the cubes, a lot of those integrals will cancel out. So imagine integrating over a face of a cube, and then integrating also over the cube right next to it, adjacent to it, over the face that actually corresponds to that one, with a normal vector pointing in the opposite direction. Those two integrals will disappear. And at the end of the day, once you add up all these 6 integrals for all the n cubes, all that will remain out of this operation are only the external faces of the cubes close to the boundary. And that will be equivalent to saying v dot n, the integral over the boundary surrounding omega of v dot n. And this is Gauss divergency theorem. This right here is one of the most powerful equations and identities in mathematics, because it allows you to take a volume integral, an integral over the internal portion of this volume, and turn it into a boundary integral. So you submitted all the information of v, whatever that field is, you're actually sending that information over to the boundary only, so you can get an equivalent or a corresponding value of the effect of what happens in the interior by only using information on the boundary. Okay, that is very powerful, and the power of it will become apparent very soon when we use this in the opposite direction. Because in the opposite direction, if you have a boundary integral, which in physics comes up all the time, when you do an energy balance, for example, you say, well, whatever comes in is equal to whatever comes out, or whatever comes in minus whatever comes out is equal to something else. That is in the form of a boundary integral. And if we can somehow turn that into a domain integral, then we have the hope of actually building a differential equation for that particular problem. So this equation right here, known as Gauss divergency theorem, is very powerful. Now, again, it applies to any field V that traverses any region omega, that is bounded by, there's something that I forgot here, that is bounded by gamma. Gamma is the surface that surrounds omega. Okay, now this applies in any number of dimensions. If you do this in 3D, then this will take on the, see, this is written in general, regardless of the dimensions of omega and gamma. If this is a 3D region, this will be the integral over a volume, the triple integral over a volume of the divergency of V over that volume is equal to the integral over the surface. It has to be a closed contour integral for this to work, of V dot n d gamma, or d surface, I'm sorry. It's the same thing. Gamma is the generic name for the surface that surrounds the volume. We can do this in 2D. So in 2D, the region omega would simply be the integral over some area of the divergence of a vector field that traverses that area. Differential of area is essentially equal to the integral of the line C that surrounds that area, dc. And we can even send this back to 1D. In 1D, this will be the integral from a point A to a point B of the u dx. So we're basically integrating over a line, and the divergence of a vector field. Vector field doesn't exist anymore in 1D, it's just a scalar. And we just call that scalar u. It's equal to what would be the line integral. If the domain is one-dimensional, then the boundary of a one-dimensional domain is basically 2 points at the end of that domain. And that would be u at b minus u evaluated at point A. That's it. Those are 3 equivalent or specific versions of Gauss divergence theorem. All right. So what I'm going to do now, let me go to another set of notes that I have here, because I want to jump to something that is very important too. All right. So now let's say that I give you the following. If we write again the Gauss divergence theorem, the integral over omega, divergence of v, whatever v is equal to the integral over gamma, v dot n, d gamma. Okay, again, remember, omega can be 1D, 2D, or 3D, and then gamma will be 0D, 1D, or 2D to that corresponding omega. Now let's assume for a moment, that we can write v as the gradient of phi. Okay, and later on we'll see when that assumption is possible. But let's assume for a moment that we can write v, that vector field, as the gradient of a scalar potential. Okay? Remember, the gradient of a scalar becomes a vector field. But let's assume that we can do that. Okay? It is at least dimensionally congruent, because if phi is a scalar, we take the gradient of it, we get a vector, and so we can have that. If that's the case, then this would be the divergence of the gradient of phi, d gamma, is equal to the integral over the boundary of omega, which we call gamma, of the gradient of phi dotted into the normal vector, d gamma. Okay? Now, remember that this operation, the divergence of a gradient, we call the nabla square, or the Laplace. So the Laplace of phi, so the integral of the Laplace of phi is equal to the over omega is equal to the contour integral of, well, the phi grad phi dot n. We call that the normal derivative of phi. Same thing. Remember when we define normal derivative. And this is just another version of Gauss divergence theorem that is going to come in handy when we do some derivations. So that's again another version of Gauss divergence theorem that's very important. But in order to arrive at these, we had to make the assumption that the vector field, this is the original version of Gauss divergence, that vector field had to be equal somehow to the gradient of a scalar potential, but again, or scalar field. This is potentially congruent, again, dimensionally congruent, because phi is a scalar and v is a vector, and the gradient does that. So we plug it in here and we obtain this. Later on we'll see when this is possible, but it turns out that whether this is possible or not to convert a scalar to a vector, or have a vector coming from a scalar, this is always true, no matter what. If you have a scalar potential, you can always say that the integral over a region, a closed region, of the Laplace of that scalar is always equal to the closed contour integral over gamma, which is the surface that surrounds a region omega, of the normal derivative. And again, we're passing information over to the boundary. So this is always true. As this is always true, this is always true. Okay. So let's see when this Gauss divergence theorem comes in handy. So let's look at, for instance, let's talk about heat conduction. So I'm going to reference this to, again to a physical problem that is relevant to us in engineering. And let's again assume a region omega. And within this region omega, we have temperature, which is a function of x, y, and z, right? And that temperature induces a heat flux. So because of that temperature, we have a heat flux Q, which is a heat flux vector, which is minus k grad of T. Okay. So what we're going to do is say, apply first principle. Apply first principle. And first principle is nothing but saying that the amount, in this case, of energy going out minus the amount of energy, going in minus the amount of energy, in this case energy rate, going out, plus the amount of energy being generated is equal to the change over time of the energy within that control volume within omega, which is the storage. All right. And let's assume, for the sake of argument here and for the sake of illustration of this particular problem, that there's no generation in omega. There's no energy generation. So that means that this domain is not chemically active. There's not an exothermic or endothermic reaction going on. It's not nuclear reactive. There's nothing going on. There's no electrical resistance inside, and there's no current passing through those electrical resistances that would generate any energy or that would consume any energy. So for the sake of argument, let's say that this is a passive domain, just a piece of metal, right, through which we have some temperature distribution. The temperature distribution induces some heat flux. So let's say that that's zero. And for the sake of argument too, let's say that there's no storage. So let's say that this is undergoing steady state. And that means that this is zero. Okay, so when there's no storage, that means that all the partials with respect to time go to zero. Okay, there could be changes from position to position, but no changes in time. Essentially, this is in steady state mode, it's in cruise control. Whatever was going to happen on this domain, it already happened in a state like that forever. Okay? And this means that all generation quantities go to zero. All right. So now we're confronted with these. Energy rate going in minus energy rate going out should be equal to zero. So energy has to be conserved by the amount that goes in and the amount that goes out. By the way, this first principle applies to everything, not only energy. Anything you want, you can apply first principle to. Right? You can apply these to mass, for example, and come up with the conservation of mass equation. You can apply this to momentum, linear momentum, and come up with the equations of motion. You can apply this to angular momentum and come up with the equations of angular motion. You can apply this to money in your bank. You know, the amount that you deposit minus the amount you take out plus the interest that is generated is equal to the amount that is accumulated in your bank account over time. Okay, it works. This always works. All right. So just for the sake of argument and illustration, we're applying it to heat conduction because it's something that we mechanical engineers do all the time. All right. So how do we quantify these? We quantify these by the amount of integrals, by the integral over the surface, so this is just gamma, of Q dot N, the gamma, is equal to 0. And again, why negative? Because remember that the normal vectors always, by convention, they point outside. So the out quantity will be positive, and the in quantity will be negative. So in minus out will be minus this quantity. This integral right here gives you the net effect or net amount of energy going out minus going in. Okay, there you go. So at that point, all we need to do is use this particular relationship, which is the Fourier law of heat, that says the heat flux is equal to minus K grad T. And then I'm going to just write it here so that we don't jump another page. So this will be minus the integral over gamma of minus K grad T dotted into normal. The gamma has to be equal to 0. Okay? Or another way of seeing this, if we don't want to do that yet, is we take this expression right here and directly apply Gauss divergence theorem, or apply Gauss divergence theorem. And this will be minus the integral over the volume, let's just put the minus sign here, the integral over the volume of the divergence of Q, the volume, is equal to 0. All right, so that's equivalent. Actually, I have to jump to another page. I have no option. I was trying to save some space, because we're almost at the end of it. So whichever way you do it, it really doesn't matter, because what the point I want to make here is say, well, this right here, in order for, so you can make this argument, because omega is positive and non-zero, you can always say that the integral, or minus the integral, it really doesn't matter because the minus will cancel with the 0, of the divergence of Q, the omega, is equal to 0, you can essentially say that in order for these to be true, then the integrand itself had to be 0. So in order for this integral to be 0, whatever's inside has to be 0. And again, if we apply, so given Fourier law of heat, that says that the Q is equal to minus K grad T, then the conclusion is that the divergence of minus K grad T has to be equal to 0. Now, because minus K is a constant, well, if this domain is homogeneous, it's not layered, it's not functionally graded, so K is just a value, then if K is constant, remember that K is the thermal conductivity, we can take the negative and the K outside and cancel it out. This leads to the gradient, the divergence of the gradient of temperature being equal to 0. And we know what the divergence of the gradient is. It's essentially the Laplace of the temperature is equal to 0. So this is a differential equation that we can write as the second t, the x squared, and remember x is a function of x, y, and z, no time, because we originally said that this was steady state. This was one of the conditions for these to work. x, y, and z has to be equal to 0. So this is a partial differential equation governing the behavior of the temperature field T. And later on in this class, we'll learn how to solve partial differential equations, and there you have it. So if you have a medium that has constant thermal conductivity and where there's no energy generation or consumption internally, and there's no storage, so basically in steady state, the temperature within that field is governed by Laplace's equation, or this partial differential equation. And it will be just as simple as solving this equation to get what the temperature is, obviously given some boundary conditions. You have to be given some conditions in order to fully solve this equation. Otherwise, you get some general solution, right? So you have to be told whether, well, the temperature is probably kept at a constant value around here. Maybe there's some heat amount that is coming through here. Maybe this is insulated, and so on and so forth. So once you know all the conditions around the boundary, then you can solve this equation particularly and get a temperature distribution. And this was all possible because of Gauss's divergence theorem. And by the way, we're going to be using Gauss divergence theorem a lot to come up with equations like this. Not only the equations of heat conduction, even the transient equations of heat conduction, which is called heat diffusion equation, even heat convection, fluid mechanics, mass transfer, again, momentum, and so on. Everything governed by these particular equations. All right. So that's that. So we have these. Let me see where we are. Okay. All right. Let's look at this example here. This is a useful example. I am trying to combine things from my own notes so that we sort of get a concise sequential order to these concepts. We don't jump concepts, which is what I used to do to confuse people even more, as if this wasn't confusing enough. So, all right. Now, given, let's say, we're trying to solve an example. So now, given phi of x and y being x squared plus y squared. Okay, so this is a scalar potential field and is in 2 dimensions and is given by x squared plus y squared. Now we're going to try to show that the integral over the omega over the a given region of the Laplace of this field is equal to the integral over the surrounding contour to that region of the normal derivative of phi. Okay, and by the way, we don't need to show that that works because it would always work, but it's just again an illustration example. All right, we're going to show that this is true, and if it doesn't work, it's not because this is wrong, it's because we did something wrong in the demonstration. So that, or such that, in this particular case, omega is given by let's define what this region is a circle. Okay. It's a lousy circle, but you get the point. Surrounded by gamma, and that circle has radius a. All right. Now that region, if you follow the equation of a circle, it's simply, so omega is given by x squared plus y squared is equal to a squared. and obviously omega comma gamma. Its surrounding contour is given by the circle. Omega is the area inside that circle. Okay. All right. Now, don't confuse the fact that the potential that I'm giving you is x squared plus y squared, and the region is also x squared plus y squared. That's a coincidence. It's a lousy example from that standpoint. These don't have to actually be at all the same. In fact, we could have said that this region was a square, or that region was an ellipse, or whatever it is. It just happens that in this particular example, they look like each other, but they don't have to. All right. So let's look at the left-hand side. Let's start with the left-hand side of these Gauss, or this version of the Gauss divergence theorem. Remember, this is the same thing as the Gauss divergence theorem, but extended to a scalar potential. So we need to calculate the Laplace of phi, and the Laplace of phi is the second derivative with respect to x squared of the field itself, not the region, but the field, plus the second derivative with respect to y squared of x squared plus y squared. All right. Remember, the Laplace maintains the dimensionality of the operand. So if phi is a scalar, which it is, then the resulting form is also a scalar. There's no ex or ey here. So the Laplace of phi would be equal to, then we're going to do this in steps. So first take the first derivative, which will be 2x, and then take the first derivative with respect to y here, and this will be 2y. And then the Laplace of phi would be 2 plus 2, and the Laplace of phi will just simply be 4. Okay. So the Laplace of the scalar field is a number, 4. It doesn't happen all the time, but it just happens to be the case. All right. So what we're going to do to solve the left-hand side, again, is take the integral over omega of 4 the omega. Okay, that's pretty simple because this is basically the integral over an area in the xy plane of 4 differential of area and the xy plane. Okay, because I'm going to write it here. This is dy, this is dx, and this is the differential of area and the xy plane, which is dx dy. As simple as that. And you can recognize, you can do this very easily because you can take the 4 out, right? And recognize that the integral over the area is just simply the area of the region, and the area of the region is essentially the area of a circle, which is pi r squared, and r is equal to a. So that's very simple, but we're going to do it formally. This is going to end up just simply working out as being 4 times pi r squared. Let's see how this is actually done. So we're going to do it from scratch in case the integrand is not a number that we can take out. If it's anything else, then we have to formally state what the differential of area is and so on. All right, so the left-hand side is equal to the integral from x1 to x2, integral from y1 to y2 of 4 dy dx. It is very important that the limits of integration of y correspond to the internal differential, and the limits of integration of x correspond to the outside differential. And if we plot this, let's just look at a piece here of the first quadrant, for example, x, y, and let's say this is the circle that would go from A to A. This equation right here, y is equal to the square root of a squared minus y squared minus x squared, sorry. And by the way, if you keep doing this to the fourth quadrant, then this function is slightly different. This function is minus square root of a squared minus x squared, right? Just remember, the original function was x squared plus y squared is equal to a squared, and if you isolate y, then you get the positive and the negative contribution of that square root. So if you draw a differential, so this is the differential of x. The width of these is differential of x, which is the external. Then dx, we're going to sweep this rectangle from minus a to a in the x direction, and in the y direction, the limits of integration go from y1 to y2, where y1 is minus the square root of a squared minus x squared, and and the y2 is positive square root of a squared minus y squared. All right. So the left hand side would go as the integral from minus a to a. So we're going to sweep this rectangle from minus a to a, and this is going to go from minus square root of a squared minus x squared to the positive square root of a squared minus x squared. The integrand is still 4, and this is dy dx. Okay, this is a way to do this integral. It is important again that the limits of integration of y correspond to the internal integral, because that's the way we wrote the differential, and the limits of integration of x correspond to the outside integral. Okay, we could have written this the opposite way. We could have said that this is dx dy, and then we would have to drawn that differential horizontally, and then the differential would go in the y direction from minus a to a, and in the x direction it would go from minus the square root of a squared minus y squared to the square root of a squared minus y squared. So it would do exactly the opposite, and it will work out. All right. In fact, I'm going to just do a parenthesis here. Or the left-hand side could be the integral from minus a to the integral of minus the square root of a squared minus y squared to the integral of the square root of a squared minus y squared of 4 dx dy. This would have been also the same thing. It's just this picture drawn with the differential drawn negatively or horizontally, actually swept between minus a to a in the vertical direction. Same thing. All right, so it's very important that the limits of integration of the inner integral are the ones that actually contain functionals, and the outer integral has to contain fixed numbers. Otherwise, you end up with a function. If your outer limits of integration are functions themselves, then the result of this integral will be another function, and that's not what you want. You're trying to find the contribution of this integral, and that's just a number at the end of the day. So let's continue. The left hand side. So the integral of 4 differential of y is 4y, evaluated between these two limits of integration, dx. So, which is equal to, if I evaluate y at this limit of integration, and then minus evaluated at this limit of integration, I get twice the contribution. So this would be 8 times the integral from minus a to a of the square root of a squared minus x squared dx. And now I have a one-dimensional integral. Very easy to do. Now the problem is that integral doesn't have a direct closed form solution unless you look up on a table of integrals, or unless you use MathCAD, for example, to solve that integral symbolically, which is also possible. So one way of doing it, and I'm not going to do this very often in class because this is undergraduate stuff, solving that integral. But one trick here is anytime you see an integral of something minus something squared, then you do a trigonometric substitution, and it would always work. So let's say that we're going to let x be equal to a times the sine of theta. And the reason why I arbitrarily picked that is because I want the a to go away when I square it. And I want to end up with the form 1 minus the sine square of theta, which is the cosine square, and then I can get rid of the square root. I could have just done the cosine of theta, and it will work exactly the same way. If I do that, then dx d theta, so look that I'm doing a variable transformation, dx d theta is a times the cosine of theta, and therefore dx, which is this thing here, is a cosine theta d theta. So I'm taking the d theta over to the, and then I need to modify the limits of integrations as well. And the limits of integration go like, if x is equal to minus a, this one here, then I'm going to use this relationship to convert x to theta. So then I say minus a is equal to a times sine of theta. Then the sine of theta is equal to minus 1. And in order for the sine of theta to be minus 1, then theta has to be equal to minus pi over 2. Okay, so minus 90 degrees or 270 degrees or 3 pi over 2. It will work exactly the same. So when x is equal to a, the upper limit of integration, then I use this relationship here. A equals to a times the sine of theta. Then the sine of theta would have to be 1, and therefore theta would have to be 90 degrees or pi half. There you go. So this integral right here, the left-hand side, is equivalent to saying the integral, a times the integral from minus pi over 2 to pi over 2 of a squared minus a squared sine square of theta. And outside, when we see dx, we have an extra a cosine theta d theta. All right. Again, we're making this much more complicated than what it really is. And the reason for that is because I wanted to solve that integral. Because if that integral wasn't straightforward, if it wasn't the integral of 4, and you still have to go through this entire process then. All right, so the left-hand side, if we continue here, would be 8 times. So I'm going to continue to do this in steps so that we don't confuse anybody. And this will be, we can take a squared as a common factor and actually take it outside of the square root of the square root of 1 minus the sine square of theta times a times the cosine of theta d theta. So the left hand side goes as, well, then this a and this a is a square, and it comes outside. 1 minus the sine square of theta is the cosine square of theta. So this is a 8 square. The integral between minus pi over 2 to pi over 2, and this will be the square root of the cosine square, which would be the cosine of theta times the cosine of theta d theta. All right. Now we need to take the integral of minus pi over 2, the cosine square of theta d theta. So now we need to take the integral of the cosine square, which is also not straightforward. And in order to do that, I'm going to use another identity that says that the cosine square of theta is equal to 1 plus the cosine of 2 theta divided by 2. That's very easy to remember, actually, because you can use the cosine of the double angle, or the cosine of alpha plus beta is equal to the cosine of alpha plus times the cosine of beta minus the sine of alpha times the sine of beta, and then you can work out all the identities with just one formula. Okay, same thing for the law of sines and the law of cosines. It all comes from saying the sine square plus the cosine square is equal to 1, and the sine of alpha plus beta is cosine of alpha sine of beta plus sine of alpha cosine of beta. And the cosine of alpha plus beta, it would be cosine cosine minus sine sine. So that works out very, very easily. And then you can work out all these identities directly. So the left-hand side would be 8a squared. And then this would be the integral from minus pi over 2 to pi over 2 of 1 plus the cosine of 2 theta divided by 2 d theta. Then this is broken up into 2 pieces. I can actually take that 2 outside, and the left hand side would be 4a squared times the integral, let's break this up into 2, times the integral of 1 d theta plus the integral of the cosine of 2 theta d theta. Again, I'm making this overly complicated, but just to generalize for situations in which you actually have to do this. So the left hand side will be 4a squared. The integral of d theta is just simply theta, evaluated between minus pi over 2 to pi over 2. And the integral of the cosine is the sine. So plus the sine of 2 theta divided by 2, because the integrand or the argument has a 2. And that would go from minus pi over 2 to pi over 2. And this closes the bracket. Alright, so when we evaluate theta between pi over 2 and minus pi over 2, we get pi over 2 minus minus pi over 2, which is pi, right? And when we evaluate the sine of 2 theta, it would be the sine of pi minus minus the sine of minus pi. The sine of 180 degrees is 0, and the sine of minus 180 degrees is 0. So this one goes away, 0. And here we get pi. So the left hand side is 4 pi a squared. Look at that. It worked out exactly to be the original integral. We go 2 pages ago. The integral, the left hand side was the integral of 4 times the omega, which means just take the 4 out and it's the integral of the area, which is the area itself. And the area of the circle is pi a squared. So it's 4 times the area of the circle, 4 times the area of the circle. It worked out. Okay. So let's look at the right hand side. And for the right hand side, I'm going to go to a different page. Oh no. Okay. Rip the page. All right. So the right hand side, we need to calculate the normal derivative of phi, which is the grad of phi dotted into the normal vector. And therefore the grad of phi is equal to d dx of phi, the scalar potential, which is x squared y squared. This goes in the x direction. Remember, the grad of phi is a vector field. d dy of x squared plus y squared dy. So the grad of phi is simply 2x in the x direction plus 2y in the y direction. Okay, now who's the normal vector? The normal vector is equal to some gradient of some level curves, f, divided by the magnitude of that gradient, such that the circle is given by x squared plus y squared is equal to a squared. Okay, so in order to make that a constant, remember the level curves are such that f of xy equals to a constant. So whatever we can make equal to a constant, it will work out. Actually, that constant can be any number, including a squared. So we can say that f of x and y is simply x squared plus y squared, because that's equal to a constant. Or we can say that f of x and y is equal to x squared plus y squared minus a squared, because that's also equal to a constant, which is 0, right? And that works out too. It doesn't matter what we pick as a constant, it would always work because the differential or the derivative of a constant is equal to 0. It really doesn't matter. So n would be equal to the gradient of this function. So the gradient of this function is 2x in the x direction. And again, don't get confused that this function that defines the circle is similar to the potential itself. So you end up with a function that looks pretty much the same. Plus 2y in the y direction. There you go. That is the gradient of that function. And the magnitude of the gradient of this function is equal to the square root of 2x squared plus 2y squared. All right. So the normal vector, I can take the 2 square, I can take this 2 as a common factor outside, cancel it out with these 2, and at the end of the day I will get x in the x direction plus y in the y direction, all of these divided by x squared plus y squared. So that's the normal vector. All right, so the phi dn, which is again graph phi dot n, the gradient of the potential is 2x in the x direction plus 2y in the y direction, and the normal vector, the unit normal vector, is x in the x direction plus y in the y direction divided by the square root of x squared plus y squared. So the phi dn, remember this is a scalar product. Okay, so we'll have a scalar that results out of these is 2x squared plus 2y squared to x squared plus 2y squared, all of that divided by the square root of x squared plus y squared. And therefore the phi dn, I can take the 2 as a common factor, right? And this will be the square root of x squared plus y squared. Simple as that. So the right hand side is equal to the square root, the integral with respect to gamma of the phi dn, d gamma, which is equal to the integral over the contour gamma twice the square root of x squared plus y squared d gamma. Now who's gamma? Now here's the tricky part. And there's always a lot of confusion as to how to do a contour integral. But the trick that will always get you out of these is the following. So this is a circle, and remember the boundary of the circle is gamma. And d gamma is a little bit of gamma, right? And you can always zoom in into that little bit of gamma, d gamma, and always associate it with a little piece of dx and a little piece of dy. So it would always work out that d gamma in 2d is equal to square root of dx squared plus dy squared. Okay, if you use Pythagoras, then the square of the hypotenuse is the square of the sum of the square of each side. Okay, so that will always get you out of a bind. Now the problem is that we end up with an integral of differentials that are embedded in some sort of a square root there, and how do we deal with that? So in order to deal with that, we're going to apply a little trick here of parametrizing. So parametrizing which simply means take this curve that is given by, in this particular case, this curve is given by x squared plus y squared is equal to a squared. And let's see if we can put in x and y in terms of a single variable. And in this case, it's very simple because this is a circle. And it will work out to be just simply x equals a the cosine of theta plus y is equal to a the sine of theta. If we plug these two things in here, it will satisfy this equation. That's what parametrizing means. Try to see if you can find x and y in terms of a single parameter that satisfies the equation that governs the boundary of x squared plus y squared equals to a squared. So that works out. And that means that gamma goes such that this parameter theta, which we can call another thing, we can call it t or whatever we want, goes from 0 to 2 pi to complete the full circle. Or it goes from minus 2 pi, or it goes from minus pi to pi, it goes from minus pi halves to pi halves, or as long as you complete the full circle, it will work out. Not from minus pi half to pi half, because that will be pi half, but you can do it from minus pi to pi and work out exactly the same. So then we have this d gamma, which is the square root of dx squared plus dy squared, right? And you can say that this is basically you can divide both by d theta and multiply outside by d theta. This is exactly equivalent to this, and this is what you do with a parameter. Now you turn a differential of a square root of differential squares into a formulation that has a differential outside. So d gamma is just simply dx d theta, which is the differential of x with respect to theta, which is minus a sine of theta squared plus a cosine of theta squared d gamma. And if you look at these, this negative will go away because of the square. It will be a squared plus a squared, which you can take out as a common factor as a outside the square root. And then you will have sine square of theta, cosine square of theta, which is 1. And then that simply goes like d gamma is equal to a d theta. It's as simple as that. The surface differential, or the differential of the contour, is simply a, which is the radius, times a piece of the angle. And that's just the arc length. It worked out to be exactly what we expected to be, but we did it in a formal way. All right, so the right-hand side will go as the integral from 0 to 2 pi of the integrand, which is the normal derivative of phi, which is twice x squared plus y squared, plus the differential of gamma, which is a d theta. And now we can replace x squared and y squared by the corresponding parametrization. So the right-hand side will be equal to the integral from 0 to 2 pi of twice the square root of a cosine theta square plus a sine theta square times a d theta. Oops. So the right-hand side, again, the same thing. I can take this a as a common factor and push it outside. And then this will be cosine squared plus sine squared, which is equal to 1. And then this 2 and the a and this a will be outside as 2a squared. This will be the integral from 0 to 2 pi of 1 times d theta. And the integral from 0 to 2 pi of theta, so the integral of d theta is theta, now evaluated between 0 and 2 pi. And the right-hand side then works out to be 2 pi times 2a squared, which is 4 pi a squared. And look at that. If we go back to the previous page, the left-hand side was also 4 pi a squared. So this identity works. The left-hand side, get rid of this page here, is equal to the right-hand side. Voila. So we don't need to prove that this identity is correct. The whole point of the exercise is to show that this is equal to this. But again, this is always going to work. If it didn't work, it's because we did something wrong with these integrals, which is very common, but it worked out. So this is what I wanted to show you in terms of the Gauss divergence theorem and its variants, and some exemplifications of where it can work, and use it in terms of deriving an equation, a governing equation. In this case, we did it for the equation of heat conduction. And next class we'll do it for the equation of fluid flow, and it will work out very nicely too. All right, so thank you for your attention, and I'll see you next class.